Hello, welcome back to the RedMars Podcast. I'm your host, Astro Jake, and today we're diving into the brains behind space technology, that is, processors and their components, designed to survive the harsh conditions of space. Space isn't just a vast emptiness. It's a brutal environment filled with radiation, extreme temperatures, and zero room for error. The computers running our Mars rovers, satellites, and deep space probes have to be as tough as the missions they are on. But that makes these processors different from the ones in your phone and or laptop. So how do they survive the journey through space? Well, in this episode, we're going to explore what it means for a processor to be, radiation hardened, the intricate process of hardening electronics, and the fascinating world of space manufacturing. We'll also tackle the important topic is why there's growing push to bring these components and manufacturing back into the US. What role do companies like Bay Systems and Microchip play? And what about alternatives to radiation-hardened processors? Can we really send a Raspberry Pi into space and expect it to work? Well, I bring that up only because we've talked about this quite a bit in some previous podcasts, and we're going to dive a bit more into it and talk a little bit more about the politics behind it, I guess, and what it actually means to make something radiation hardened, not just call it that. So, if you've ever wondered how we balance cutting-edge technology with extreme reliability for space missions, well, this is the episode for you. We're about to find out. What are radiation-hardened processors? Let's start with the basics. What exactly is this, and how does it work for a, processor? Well, at its core, a radiation-hardened, or what we call rad-hardened, processor works like any other computer chip. It processes instructions, performs calculations, and handles data. But unlike the chip in your smartphone or gaming console, rad-hardened processors are built to withstand the relentless assault of cosmic radiation and extreme conditions found in space. So why is radiation such a big deal in space? Well, on Earth, our atmosphere and magnetic field protects us from most of the high-energy particles from the sun and deep space. But once you leave the planet's protective shield, you're exposed to cosmic rays, solar flares, and even the Van Allen belt radiation. These high-energy particles can wreak havoc on standard electronics. And here's how. Well, radiation can cause something called single event upset, or SEU. This is when a charged particle hits a microchip and flips a single bit in memory from a 0 to a 1. Or vice versa. Imagine you're sending a command to a Mars rover and you want it to turn left. Well, a cosmic ray comes along and changes that instruction to turn right instead. These consequences could be catastrophic. You could be sending that rover over a cliff. That wouldn't be so good. So, even worse, repeated exposure can cause cumulative damage to a processor's circuits, breaking it down to the very materials they are made from. This is why space computers can't just be powerful. They have to be more reliable and last for long duration missions. So, to combat this, rad-hardened processors use specialized materials, error correction systems, and backup circuits, but the tech doesn't just stop there. So we're going to break it down just a little bit more on how the hardening process actually works. So what is the radiation hardening process? And how do you actually make a processor radiation hardened? Well, it's a multi-step process. It goes far beyond just putting a protective shield around a chip. So let's break it down. Material selection. Traditional processors use standard silicon, but radiation-hardened processors often use silicon on insulator technology, that is SOI. And that's not system on a chip. SoC, SOI. SOI chips have an extra layer of insulation between the silicon and the substrate, which helps prevent radiation from causing electrical shorts. Then we have redundant circuitry. Imagine a chip designed with multiple backup circuits. If one part of the processor is hit by radiation and fails, the other circuit takes over instantly. This concept, known as triple modular redundancy, means the chip essentially votes on each calculation. If one path gives a faulty result, the others override it. This is a voted system. Then we have error correction code, ECC. ECC memory is vital for space processors. It works by adding extra bits of data to every memory cell so the chip can detect and correct a single bit error on the fly. We've talked about this in previous episodes, and if you'd like to know more, I definitely encourage you to go back and listen to those. Shielding. Sometimes physical protection is needed. Aluminum or tantalum shields can block certain types of radiation. Though this adds weight, a major concern for space missions, it still adds some protection that can help you get past this radiation issue. And then we have design at the atomic level. The layout of transistors can be adjusted to make circuits less susceptible to radiation. For example, thicker gate oxides and wider spacing between components reduce the risk of shorts caused by ionizing radiation. This is a cool thing that I learned about during my master's in space systems, where we learned about the plasmas and arcing of components in space that are not designed to withstand that environment. So this is where materials and all that come into play, but it was cool to learn about how these plasmas can actually arc between components and more or less short them out and cause them to, well, get fried. So something that is a big issue, I guess, when moving through the harsh space environment. So I just wanted to mention that. So this process is not cheap or easy. Radiation hardening a processor can take years and even millions of dollars, but it's absolutely necessary for deep space missions where reliability is life or death. And it's not just about the design, manufacturing of these chips. It's a whole other challenge. And so this is why you have things like old 386 processors and Pentiums and stuff like that that have been radiation hardened still flying in space today because they've been proven. You're not going to really find, say, your Intel Core Ultra or Ryzen 7 gaming processor driving much in space, at least not today. And that is because they are not radiation hardened and they do not do well in the space environment. Now, you may find them in protective cases or something like that. I haven't done much looking to see if there are any of these in orbit or built on top of any rovers or anything like that. I'd be definitely curious to see, but typically you do not see those types of processors. You're looking for something that's a bit more proven, and that's the same for really everything in space. You're seeing a bit more today of first-time concepts and that being tried, mostly because of the private industry of space, which is great because this drives innovation. Now, looking at programs like SLS and Artemis and things like that, you'll find that the more traditional NASA-driven technologies, for the most part, use proven technologies, and they usually steer away from more of the fringe or research area technologies for life and death situation missions. That's not to say that they don't do all kinds of research, because they most definitely do and really push technology to the limits. However, that's not going to be the technology they're going to put on a manned mission, at least not at this point. All right, let's move on. So, where are these radiation-hardened processors made? Well, now that we know how they are hardened, let's talk about who makes them and where. So, radiation-hardened processors aren't produced in the same factories as consumer-based electronics, as you probably could have guessed. Well, instead they come from specialized fabs, often tied to aerospace and defense companies. Some of the key players include BAE Systems. They're known for their Rad 750 processor used in the Mars rovers like Curiosity and Perseverance. Then we have Microchip Technology. They produce the ATMEGA's chips, a go-to for small satellites and CubeSats. Then we have the very well-known Honeywell. They have a long-standing history of building high-reliability components for spacecraft. So, radiation-hardened processors are manufactured by specialized companies across various locations, primarily in the United States and Europe. And here's an overview of some key manufacturers and their locations. So, back to BAE Systems. Well, BAE Systems, that's BAE, operates its Semiconductor Technology Center in Manassas, Virginia, USA. This facility is dedicated to producing radiation-hardened electronics for space applications. Then we have Microchip Technologies Incorporated. They are headquartered in Chandler, Arizona, in the USA. Microchip Technology produces radiation-hardened processors and components, and their facilities in the US support the aerospace and defense industries heavily. Then we have STM Microelectronics. STM Microelectronics is a global semiconductor company that is headquartered in Geneva, Switzerland. They develop radiation-hardened components used in various space and defense applications. Next up, Infineon Technologies AG. They're based in Neubiberg, Germany. Infineon Technologies manufactures radiation-hardened electronics for aerospace and defense markets as well. These manufacturers play crucial roles in supplying radiation-hardened processors essential for reliable performance in space missions and other high radiation environments. So, in the US, there's a growing concern in ensuring that these chips are made domestically. National security plays a big role here. If the US relies too heavily on overseas fabs, it risks supply chain vulnerabilities, and something known as the CHIPS Act, for example, was aiming to boost semiconductor manufacturing in the United States, including rad-hardened processors for space and defense missions. So, with trying not to get too political on the topic, but I think it's something that we should talk about because it is in the news today and more recently. So, the CHIPS and Science Act. This was enacted in 2002 and was designed to revitalize the U.S. semiconductor industry by allocating $52.7 billion to boost domestic chip production and research. This initiative aimed to reduce reliance on foreign imports and enhance national security. However, recent developments have raised concerns about the Act's future. The Trump administration's decision to cut approximately 500 jobs at the National Institute of Standards and Technology, NIST, could jeopardize the administration of Act's funds, potentially nullifying its intended impact. Additionally, while the Act has led to significant investments, including nearly $34 billion in grants and up to $28.8 billion in loans to companies like Intel and Micron Technology, challenges still persist. These include delays in plant construction, a shortage of qualified workers, and competition from China's expanding semiconductor industry. Moreover, a report from the Peterson Institute for International Economics highlights that the government's subsidies equate to about $185,000 annually per job created, raising questions about the efficiency of this investment. All right, so in summary, while the CHIPS and Science Act was a significant legislative effort to bolster U.S. semiconductor manufacturing, its successful implementation faces several hurdles, including administrative challenges, economic efficiency concerns, and global competition. Now, under the current administration, there is a strong emphasis on reshoring manufacturing, particularly in strategic sectors like semiconductors. I'm sure we've all heard it with Taiwan and all that, so let's dive in just a little bit more. So, President Trump has proposed imposing a 100% tax on foreign-made semiconductors to incentivize domestic production. All right, well, this approach aims to encourage companies to establish and expand their manufacturing facilities within the United States. In line with these policies, companies such as TSMC, here we go, have announced plans to build advanced chip fabrication facilities in the United States, including a significant investment in Arizona. These developments reflect a broader trend of strengthening the domestic semiconductor supply chain and support various industries, including space exploration, where reliable and resilient processors are crucial for mission success. So with that, we are seeing a shift towards tech sovereignty, making sure that the future Mars missions and moon bases have reliable American-made components. And it's not just about reliability, it is also about security. If you do some research on that, you'll find there's been several instances where there's been backdoors found inside of microchips used in some of the most sophisticated defense equipment in the United States. And by backdoors, what I mean is the ability for a foreign nation to gain access to those microchips in a domestic military aid or equipment while being in that foreign country. So imagine hackers from China or Russia being able to get control or gain insight into, say, an F-22. Not a good thing to have. So these vulnerabilities are a result of foreign parties making processors for our defense and security systems. So I definitely agree with wanting to bring some of this back to the United States, especially where security and safety of personnel comes into play. So, all right, enough about politics and all that. Let's talk about, are there any alternatives to radiation-hardened processors? Well, we have talked about this in our talks about space computers and CubeSats and all that, but we're going to go into this just a little bit more this time. So not every system in space uses radiation-hardened tech. So let's see where or how sometimes the use of commercial processors in orbit makes sense. So, what are the alternatives? Believe it or not every single piece of tech in space is radiation-hardened. We've mentioned this. So, CubeSats and experimental missions often use commercial off-the-shelf COTS components like the same processors found in consumer devices. This might seem risky, but it does come with some advantages, one of those definitely being cost. Radiation-hardened chips can cost hundreds of thousands of dollars, while COTS processors are relatively cheap, sometimes, in the tens of dollars. So, then you come with innovation. This is what I kind of mentioned. Radiation-hardened typically are older architectures, older technologies. So consumer tech evolves much faster. So using a COTS processor lets mission tests the latest technology. This is very similar in the aviation industry as well. You go and buy a aircraft that is certified, you're going to end up with something like a Cessna 150 or Cessna 172 that could cost you anywhere from $30,000 to $200,000. That airplane's been flying a long time. It has been proven. It's a great aircraft. Then there comes the experimentals. You can end up getting something like a Van's RV-8, super fast, sleek, state-of-the-art aircraft. It has glass cockpit, a stick between your legs that allows you to pull mean G and aerobatics and all kinds of stuff. Far from a Cessna. You can get a kit for, $40,000 plus the cost of an engine. And in the end, you're still well under the cost of a brand new Cessna 172. And you end up with a lot more aircraft. Now, the difference is it is not a certified aircraft. So there is risk that comes along with that. But in today's day and age, there's a lot of very well-built parts and manufacturing processes have come a long way. So these types of aircraft, I would say, in my opinion, are far less risky than they used to be. And you get kind of the best of both worlds. New technology, cheaper aircraft to purchase, and a lot more fun. Not to say there's anything wrong with a Cessna 150 or 172, but anyways, we'll get off this tangent here. So next up is redundancy. Instead of hardening one chip, some missions send several, using software to detect and isolate failures. However, these systems typically operate in lower orbits where Earth's magnetic field offers some protection. NASA's PhoneSat project, for example, used Android smartphones to test small satellite capabilities. So while rad-hardened processors are crucial for deep space missions, COTS processors help drive innovation and reduce the costs for low Earth missions. That is Leo.
I'm a Leo.
All right, so what's up next for space computing? Well, we're seeing that shift not just towards more powerful processors, but also in how and where they are made. With the growing push to bring chip manufacturing back to the United States, the future of space exploration could depend just as much on what happens here on Earth as it does out there in the stars. Well, that's all I got for all of you today, so thanks for tuning in to the RedMars Podcast. If you enjoyed this deep dive into processors and space tech and all that, don't forget to follow, rate, subscribe, share all the fun stuff, and stay tuned. And until next time, I'm Astro Jake. Keep looking up, stay curious, and enjoy the rest of your week.